Sorry. Like
That's 1, 2, 3.
wait. Oh. Yeah, I would actually do it.
All right. Well, welcome everyone. We have a guest here today. Rosa, you want to introduce yourself to the entire class? Excited to see you all as usual. We're going to cover actually our last basic formulation today. No, not our last one. We've got gradient equations after this, but nearly our last basic formulation. And this is a super important one that we're going to talk about today. We're going to talk about Michaelis-Menten kinetics. What could be more exciting than talking about Michaelis? How many of you, when I say Michaelis-Menten, how many of you are like, what the heck does that mean? And what the heck does that mean? Right. Okay. How many of you know what I'm saying when I say Michaelis-Menten? Okay. Shakily, Jackie shakily knows what I'm saying. You were an enthusiast. They're like your Led Zeppelin. All right. I got that. All right. So anyways, this is another analogy that, like many of our analogies, comes from chemistry. Chemistry turns out to be the source of many fine analogies for us biologists and ecologists and people thinking about the world as a whole. This particular one is useful for saturating phenomena where something increases as one thing goes up. And in chemistry, you talk about it as substrate concentration. So as your substrate concentration goes up, your reaction rate goes up until it's no longer limited by that substrate, at which point it levels off. And so more than Michaelis-Menten, I tend to refer to this as hyperbolic saturation, because it's a hyperbole. And there are so many phenomena that work this way. It's just an enormously powerful analogy and metaphor for many, many things. As someone who spent a lot of time thinking about photosynthesis from like a scientific standpoint, this is probably the most common formula used to model the response of plants to light intensity. So as light intensity goes up, photosynthesis goes up, and eventually, and this can occur at several different levels of organization. So a photosystem can saturate, and more light no longer means more photosynthesis, because it's got all the light, it got all the energy it is capable of sucking in, and adding more light energy at that point does not actually help it at all. It doesn't do anything else with that light energy. But more generally, if you think about plants or really any organism, we tend to be subjected to limiting factors. At any given time, there's something limiting us from doing more of that thing that we would like to be doing, right? Whether it's photosynthesis, whether it's growing, whether it's doing just about anything, whether it's getting work done, whether it's getting homework done. At some point, if you have no work in your life to do, you will get no work done because there's no work for you to do. As people begin to give you work, you will start to get work done. As they give you more work, you will get more work done. As they give you yet more work, eventually you're going to be like, I can't get any more work done. And that's sort of a saturating rate at which you're getting work done based on the substrate being worked. But going back to plants for a moment, plants are limited by many potential things. What potentially limits plants? Nutrient availability is key. Nitrogen, phosphorus, potassium are the key macronutrients for plants, but then there's a lot of other micronutrients which are really important to them. Yes?
Sunlight availability.
Sunlight availability. What else? Water. So those are three, and potentially a lot more if you're counting different nutrients. Those are multiple different factors which might limit the rate at which a plant grows. So any one of those can be a limiting factor acting on plants. So this hyperbolic saturation function equation is very, very useful. We're thinking about any situation in which there are limiting factors involved in the growth of something. And what's very, very important to understand, and also somewhat confusing for people to grasp, is that this formulation is totally unlike any of the formulations we've dealt with so far, in that this is not a relationship between some stock and time. This is not a time graph here. This is a graph of a dose response relationship where you're giving something a dose of something it needs, and it is its response rate. So this is not, unlike everything else we've talked about so far as our basic formulations, hyperbolic saturation is not a differential equation itself. It is not a growth equation. However, it's very often a modifier for a growth equation. So it's a modifier where you have a certain growth rate. So you think of your very basic first order type growth situation where you've got growth which is proportional to stock size. And we've had our basic population growth R times N, exponential growth, first order growth. So this would be a modifier that you would throw in there saying, in an ideal situation, you'd have R times N, but they're not reproducing as fast as they might be reproducing because they're limited by one or more limiting factors, which is constraining R. So think of R as sort of the maximum growth rate, and this is the thing that constrains maximum growth. And I'll get back to all of this. I'm just trying to give you sort of some big picture context up front for why this is important and how it's used. So it is not itself a differential equation, but it is a modifier for a differential equation that's very, very useful in any situation in which you've got a limitation on how fast things can happen because there are one or more limiting factors involved in them. Okay, so that's the introduction, and then I'm gonna dive deeper into it as we go because it's got some different important pieces and parts. We'll get into those. The different important pieces and parts. I'm going to get ahead of myself. I'm just going to go ahead and say it. There's some maximum, which is sort of like the fastest it can possibly do what it's doing, Vmax, velocity max. So we often refer to it as Vmax, or if it's photosynthesis, Pmax, P for photosynthesis. But it could be Rmax, maximum growth rate for some population. And then you have a constant that we often refer to as Km, or Kn, or K whatever. This has different things, so we often refer to it as K. And this is referred to as the half saturation constant. So when people talk about hyperbolic saturation, it'll have two key parameters. You guys are onto something here.
Let's see. We've been
You've been talking about this. Oh, well, here's what I'm going to say, and I often have. So I'm going to tell you straight up, chemistry is useful. I have had so many students take my classes and have these aha moments somewhere through my classes where they say, "Oh my God, chemistry is useful. I had no idea that chemistry is useful." And I'm like, "Yes, it's useful. Yes." I feel like sometimes chemists are so enamored of their field and don't recognize that there are many people taking their courses who are not of their field, that they don't always, I think the chemists are not always the most convincing people in helping people to understand how cool chemistry is. I know that's an odd thing to say, but I just feel like it's true. Like we compel our environmental studies students to take chemistry, and they say to us, "Why do I have to take chemistry? We don't like chemistry." And then they'll take one of my classes and they'll say, "Oh my God, chemistry is super useful and important." And I'm like, yes, it is. Yes, it is. Yes.
Yeah, and I've had the exact same experience here. It's like you must why are the chemistry teachers not saying this?
It's because their heads are too inside of chemistry. I think you have to sometimes, honest to God, I'm serious. I don't mean that. I mean, there are people who just appreciate the beauty elegance of chemistry as something in and of itself, and all respect to those people. But there are a lot of us in the world who are just practical people. We're trying to just get stuff done, you know, and for us, it's like, we need to know how is it useful before we can, like, you know, understand that it's beautiful and elegant. And maybe we'll never understand that it's beautiful and elegant. Maybe we'll always feel like it's a tool. It's like a circular saw or, you know, a drill press that you use to get stuff done. But it is very, very, same with stats. Stats is incredibly useful, but it can also be boring as sin if you're just taking the stats book. You know what I'm saying? But you love stats.
Make my brain.
The statistics make anyone else's brain feel like a happy horse experience. All right. Well, I'm gonna go ahead and straight up. I'm just like stealing all the thunder from things I would say later, but like, well, let me ask you guys, why is it called the half saturation constant? Why? Why half saturation? All right. You guys want to answer, Jackie? Why is it the half saturation?
It's at one half of the max, there's a certain like reaction velocity that's going on. And that is always aligned with a very specific amount of substrate. So it's a nice place for consistency. Yeah, and it ends up being important in the equation. I'll tell you how I remember it. This initial slope here, so this initial slope, the linear portion of this slope has a special name. Do you guys know what that name is? It's called alpha, at least in my world, it's called alpha. Okay, tell us about that. No, I like the insight though, but no. That's different, and I don't want to get into that because it'll confuse people. But if I took this alpha and I stretched it out and made it cross the line where saturation occurs, so if I took that initial slope and took it up there, the half saturation is, and then I drew a line down from where this line intersects. The Km would be half the distance between those. So that's why it's called the half saturation, because like I say, if I took that line, put it up here, and then drew a line down, it would be at twice Km. It would be the full saturation. So that's why it's called half saturation, because it's at half of that value. And I don't think I even normally tell people that, but you guys seem like an interested bunch, so I'm sharing that with you. Okay. Right, so we are now on Michaelis-Menten, and I don't know why I have this in red here. Well, we kind of did gradients when I didn't quite make it through our dam model, but that's a gradient. But we're going to come back to gradients in a week. But I'm going to say something I said yesterday, and it's kind of a repeat of something I've said today, which is in this class, we do graphs of things against other things. And last time at the close of class, I introduced you to one of my favorite things, which is a phase plot, which is a very cool thing. So oftentimes we're graphing stocks versus time. This is a dynamic simulation modeling class, so we're looking at how state variables, things that define the state of a system, change over time. And then I said another thing that we're interested in is dose response graph. So that's what we're on today, is dose response. The Michaelis-Menten is definitely a dose response type situation. And then last class, we talked a little bit about graphing two stocks which are interacting with each other against each other. And like I say, that's a super cool thing to do with predator-prey interactions. If you get into systems theory, what we saw the other day with the predator and prey kind of like basically chasing each other around that circle, that is called a cyclical attractor, because it's kind of, there's stability in that system, but the stability is a cyclical stability. So we did talk about cyclical stability the other day, but you'd refer to that graph, that phase plot that's forming that weird egg shape, as a cyclical attractor. There are also oftentimes point attractors where you'll get like a spiral going into one
permanent steady state type of situation. Actually, I think one of our initial population models, there was oscillation that damped. You remember that? I think the turtle model, where it sort of damped over time. That's a point attractor. We didn't do a phase plot in that, but if you had plotted human population and turtles in that, you would have seen a point attractor where it spiraled into a point and achieved that sort of stability in the point. So anyway, that's a little bit of an aside, but one I thought I'd share with you. So like I say, there are several different kinds of equations that we talk about in this class. We started to talk a little bit about how just about everything we've done so far is working with differential equations. You know, how does some stock change over time? And, you know, simplest form, first order growth type situation. There are also, and we'll talk more about this later, there are analytical solutions to differential equations. So some differential equations, and those of you who've had calculus and remember calculus, you'll remember that you could sometimes, like this particular equation has an analytical solution, which is what this is. So n at times t equals your initial condition, n0 times e to the RT. This is the analytical solution. Now, we will spend almost no time in this course on analytical solutions, because as soon as you have any sort of complexity in terms of multiple stocks interacting with each other, there tends to be no analytical solution. There is no analytical solution. So simple first order growth and loss, they've got analytical solutions. People who are real calculus cognizati can come up with analytical solutions to more complicated equations. But once you get into having multiple stocks in a model, there's never an analytical solution. Like all of these models of global climate change that we use, that the IPCC, the Intergovernmental Panel on Climate Change scientists use to predict the future, those are like analytical solutions are so out of the question on those because there's so many interacting variables, just not a thing. And so we use, and we'll talk more about how Stell is doing this behind the scenes, we use numerical solutions rather than analytical solutions. Numerical solutions to differential equations is what Stella is doing. It doesn't use an analytical solution, but there are analytical solutions to very simple equations. And then there's sort of dose-response relationships. And like I say, today we're talking about a dose-response relationship in which we're not expressing the change in something over time, we're expressing y as a function of some variable other than time. And as I say, oftentimes we're using these inside of differential equations, but they are not themselves differential equations. And I just want to make that point. So let's see, just so that I begin to get you thinking about dose response relationships, I want to give you a second to just sketch out your thoughts on these stimulus response type variables. Like what would you expect to see happen in these different situations? So this particular one, by the way, is it's births as a function of age of how many births are happening per people at different ages, just so that that's clear. This is not time, this is age. But yeah, so take a moment to sketch out your thoughts on these particular relationships and then compare notes with your neighbors. Just want to emphasize once again, I'm not asking for anything about time in this. It's a question of like It's a question of an independent variable that is not time versus rate versus some sort of thing. Yeah.
Yeah. So I would expect it to.
That's true.
Yeah.
I'll buy that. Was that said to me or was that just said to the world?
I was being. Put a plant in the dark with a space heater, temperature doesn't affect.
That's true. Fair
But
point.
that's obviously.
Yes. It is going to affect respiration though. That.
Yeah,
The plant is definitely feeling it.
yeah. It'll do work.
Yeah.
But I mean, it's.
I guess it would maybe, you would hit a certain temperature.
All right. Enough of that. All right. So some thoughts here. Rate at which you get work done versus the amount of work you have to do. Again, you have to sort of think about this not as a time phenomenon. This is a general situation. This is like if I measured you over the course of a semester and I asked you how much work you have and how much work you're getting done. And if I did that with a lot of people, I'm getting a general equation here versus amount of work and rate at which work is done. What would you expect this to look like for you or someone else? Yes, go ahead.
I would expect to see an initial increase that speed. And then
Yeah, because if you have no work, you will get no work done. So it will go up from 0. Yes. So this is an example of a hyperbolic saturation type situation. Now, one thing I haven't introduced here, which is not in the Michaelis-Menten equation, but is in some more sophisticated equations that are hyperbolic saturation, is something that happens once if you keep piling stuff on, like light. Like what happens to a plant? You keep on dumping light on it. Yeah, it begins to crash. And does anyone know what the word for that is with photosynthesis? It actually has a special word. It's called photoinhibition. You reach a point where your photosystems actually begin to collapse because they're just too saturated with energy. But anyway, we think about a saturation, and you can imagine that happening with work where you're just completely overloaded. You're like, and you just don't put anything done. Okay, so pain and ibuprofen taken. I actually don't really. This one you have to think about as in a generic situation of a dose and pain. So what would I expect on this one? Any thoughts? Yes, go ahead, Jen. Yeah, okay, so you're thinking about something like that. And maybe at some point you take so much that I don't know what too much that does to me. So and that's kind of a long-term phenomenon as opposed to a short one. I suppose I'm sure there are people who OD'd on ibuprofen and killed themselves, but I don't know quite what it would do. What's that? A hole in your gut, yeah, also, which would be painful. Yeah, all right. Births, age. What do you expect this one to look like? Jay?
I'm trying to make a very
Yeah, I think so. And of course, it depends on the organism you're talking about, but for human beings, almost certainly it looks like that. Yeah, so that makes sense. That's good. So different shapes here. Temperature and photosynthesis. I used to include temperature as a basic formulation in this class, and I just kind of ran out of time. It's the equation you use for that is called the Arrhenius equation, which is a model of reaction rates as a function of temperature in biological, also chemical systems, but I don't do it anymore because it's too much work. And not enough payoff. So what would I expect what do I expect? How do I expect, any organism that's growing to respond to temperature? Yes.
It would be very similar to so with sort of a harsher cutoff at a certain point. Yes, so initially having more temperature to a certain point helps photosynthesis happen faster. There's more energy, the plant is at a better temperature, and then at a certain point the plant closes. Or it has to close its stomata, so it can't do business.
Yeah. I think most people think about most biological responses to temperature as they do exhibit that, but people usually think about, mostly people model them as being more just what is this? What do I call this thing? Normal shaped curve. Yeah, where there's what's called a temperature optimum for a given organism, for a given process, and different plants actually have different temperature optima for photosynthesis. Actually, interestingly, it turns out that photosynthesis is less temperature sensitive than respiration. So respiration is goes up faster with temperature than photosynthesis does. So
Respirations have to be
well, if you think about net photosynthesis being gross photosynthesis minus respiration, as you increase temperature, photosynthesis tends to go down because respiration is going up, not necessarily because photosynthesis is really not necessarily because gross photosynthesis is going down, it's net photosynthesis is going up. It turns out, interestingly, that that photovoltaic cells also have a temperature light response, and the production of solar arrays. This is something that I guess I could have learned because someone could have taught me it, but they didn't teach me it. And this is something I discovered when I was first analyzing data on the Lewis Center's solar array, which was the largest solar array in Ohio for 10 years. When I was analyzing it, I'm thinking to myself, oh, I'm going to see peak production on around June 21st, the solstice. Is it the solstice? Yes. It's confused. It is the solstice. Yes. June 21st, June 21st, June 22nd. The spring solstice, summer solstice. I was thinking I'd see peak production around then. I did not see peak production around then. You see peak production in May, the highest possible production. And it's because the photovoltaic cells themselves don't behave as well when they're hot. So even though the integrated light production over the course of the day is maximized around June 21st, it turns out their productivity is not maximized then because there's nothing a solar array likes better than good sun, but with cold. They do better. They perform better. So you get your peak production days, and not dissimilar from plants. Probably some of the same physics going on.
Why is it?
I don't know. There's something about the more heat that just the sort of excited, electrons in the silicon wafer, the doped silicon wafer, which is about as far as I like to go into how solar cells actually work, are unhappy when it's hot. They don't perform as well. So yeah. So photosynthesis versus light, obviously we talked about hyperbolic saturation, nutrient concentration. This is a longer term reaction because the plant's responding to a longer time period for nutrient concentration, but also hyperbolic saturation type relationship. Okay, good. So got you guys thinking about dose response relationships and how they are in fact different for different things, depending on what the thing is you're talking about. So that's important. Just to remind you guys, there are two different kinds of stability that we talked about, and I've made quite a fuss about this in this class. So I do hope that you remember this. There's equilibrium, which is lowest energy configuration, and then there's steady state. So these are two situations in which you can maintain constancy in a system over time. But in biological systems, as I've said many times, they're necessarily open to energy input. So stability in biological systems
is actually contingent on constant energy through flow. You need the energy through flow. So what we're trying to achieve in our lives is not equilibrium. We're trying to achieve steady state in our lives. So that's what we're shooting for. And I said all this before, so I'm not gonna spend more time on this particular slide. So we've talked about catalyzed reactions, about how a catalyst can lower activation energy and cause a reaction to happen that wasn't previously happening. So that's a thing. And, a catalyst is some sort of bonding sites. Your reagents come together, they form a bond in that, and then they break apart and find a new thing. So it's just a substance that increases rate of reaction. We talked about enzymes as sort of like, biological catalysts that control just about everything going on. And they're just sort of lowering the activation energy. By the way, I find activation energy itself to be incredibly useful analogy for many, many, many things in this world. And so does Gigi. So there you go. I just find it to be a really, there's so many phenomena where there's just a barrier you got to get over, and if you can lower that barrier, I think it's got a lot of psychological applications, actually, the concept of activation energy. And I think I'm turning to Tom, who's our class psychologist in the room, or psychology major anyways. In a lot of sort of community-based social marketing, what we're effectively trying to do is what I would call choice editing. Make it easier, reduce the activation energy necessary for people to exhibit behavior that is pro-environmental or pro-community. We're just trying to lower that, the barrier necessary to do that, and thereby get more of that reaction happening. So that's very commonly what we're trying to do. And talked about enzymes a bunch now. And they're super important. And you've probably seen lots of things like this. This is the so-called lock and key hypothesis of enzyme catalyzed reactions, where an enzyme has an active site on it, and their reactant fits into the active site, forms an enzyme substrate complex, and then the enzyme substrate complex does its thing. And you could be breaking things apart, and you could just as well, the catalyst could be doing either things, causing things to break apart or causing things to come together. It's just, that's what catalysts do. That's actually, that lock and key hypothesis is not actually that old a concept. But it's important because when we talk about the Michaelis-Menten reaction, it really comes from enzyme catalyzed reactions or just catalyzed reactions in general. That's where it's derived from. So we talk about an enzyme and a substrate, ENS, forming an enzyme substrate complex and then breaking apart to form the enzyme and its product. So that's kind of like, that's context for this. And it used to be for probably the first, I don't know, maybe 6, 7, 8 years that I taught this class, I would go through the full derivation of how you can come up with a Michaelis-Menten equation based on sort of equilibrium principles in chemistry. I'm sure you guys probably just did that in chemistry. You probably at some point walked through how you derive Michaelis-Menten. Is that true? Is that what you're doing in 102? Right. And you probably will, if you haven't walked through it, you probably will walk through it. And one of the things I discovered along the way in these 8 years of doing this derivation is there are some educators who are gifted at entertaining people doing mathematical derivations. And I am not one of them. I just feel like I bored the class to tears doing it. So I no longer subject you guys to the derivation of this equation. I will walk you through some of the slides I still retain for this, but only to illustrate the point
that you can derive the equation, not in the hopes that you will actually follow me deriving the equation, and not with the expectation that you will reproduce the derivation of that equation on any quiz I will ever give you. So I'm just going to say that just as a preface, because it didn't work for me and it definitely didn't work for my students to derive the equation. So I'm not going to do it. I'm going to cut to the chase and say, this is the equation, and it's a really, really cool and simple equation. It's just incredibly cool what this very simple equation can do. Let me just say what we're looking at here. So this is some reaction rate, right? So this is in fact a differential equation, it's some reaction rate. And that reaction rate is equal to a maximum reaction rate, V max, times this little very simple, equation here, this little tidbit here. And this little tidbit here is just so damn simple and so damn cool. So this is my substrate concentration. This is the limiting factor here. So S is whatever is limiting this thing. And Km is the half saturation constant. So obviously the units for substrate and the unit for the half saturation constant are the same because we're adding them together. And this is what is so cool about this. If you think about this in the extremes, this equation makes a lot of sense. When S is much, much larger than your half saturation constant. So when I'm way out here, when Km is down here and I'm way out here, if S is much, much larger than my half saturation constant, what does this little part of the term become if S is much, much bigger than Km? It becomes 1. If this is a really tiny number, then a giant number over a giant number plus a tiny number is 1, right? So when I'm way, way bigger than K sat, I'm at V max. That's when I flatlined, right? So I can put more substrate in and it doesn't make any darn difference. Whereas when S is much, much smaller than Km, basically my maximum rate of reaction is proportional to substrate, because then this becomes irrelevant on the bottom. And it's just sort of, I've got substrate over some constant. And the more of that substrate I have, the faster this thing is going to go. So this, when S is much, much smaller than Km, I'm in the linear portion of this curve where this is basically just a straight line. So this, yes, limits. So you're going to get a lot more experience with this, but I just wanted to say that straight up because that's the beauty of this equation is it does, and then when they're near the same size, that's when I do this lovely transition up here. Yes. Yeah, I absolutely will. So this is how fast things are going. It's the reaction velocity here. So it's how fast my system is doing its thing. V max is the maximum rate that it can do its thing. So when it's honking, like you've got a car, you put the pedal to the metal, it's got a maximum rate that it can travel. It's not going to go faster than that. It's saturated. So you put your foot down on the pedal and you're going faster and faster and faster. And then, it's just gonna, so Vmax is the maximum speed of the vehicle. This is some sort of limiting factor. Could be light, could be nutrients, could be a bunch of different things. And so that's what's on this axis here is my substrate concentration. And then Km is just a constant. It's a constant that defines how curved this is. If my Vmax is larger, this curve is going to stretch out. If my Vmax is smaller, it's going to saturate more quickly. So it's going to do that. And super relevant because organisms actually evolve. They will evolve based on either Vmax or Km. Like if you're a plant living with unlimited sun, so you're not in the shade, you're a sun plant. What you're trying to do, your evolution, your genes are being selected for by trying to bump up Vmax as much as you possibly can. Whereas if you're a plant living in with lots of trees above you. So you're a understory plant in a dense tropical rainforest, let's say. There's not that much light down there. You're evolving to make your KM as steep as it can possibly be, so that you can get as much light out of as little sunlight as you possibly can. So if you're a shade plant, you're evolving with KM being your primary sort of evolutionary pressure. Whereas if you're a sun plant, you're evolving with Vmax being your selection pressure. Does that make sense? So like really, plants are, I'm saying, if you're plankton that live in the bottom, you're doing that. If you're plankton that live in the surface, you're doing that. And actually, if you're plankton living in the bottom, you're actually evolving to take advantage of different wavelengths of light, because all of the good blue and red spectrum that is most useful for your photosynthesis in a generic sense is being sucked up by the plants above you. So you're developing pigments, not just chlorophyll, but other pigments that can take advantage of other wavelengths of light. So if you're living in the bottom, a little bit of an aside, but just saying it's different if you live at the bottom than if you live at the top. Michaelis-Menten formulation, it expresses reaction rate as a function of substrate concentration. As substrate concentration increases, reaction rate increases and achieves some sort of maximum. Now, in classic kinetics, what's happening is your enzymes are saturating. Your enzymes are getting, basically all of your enzymes are full of substrate at some point. And so adding more substrate doesn't help you out, because all of the enzymes are, all of the active sites on the enzymes are occupied. That's why it's derived from enzyme reactions. And again, I'm just reiterating what I said before. When S is much, much smaller than Km, then basically reaction rate is proportional to your substrate concentration, the linear portion here. Whereas when S is much, much larger than Km, then you're basically just going to exhibit your maximum velocity of reaction rate. You guys good with that? All right, so here's the part where I'm going to sort of breeze by the actual derivation. But just to say, like, what we're trying to do here is take just the information that we've got enzymes, we've got substrates, we've got enzyme substrate complex, we've got a product, and we've got reaction rates that are going on here, a forward reaction for this and a reverse reaction for this same equation. And again, this is where you can kind of just look at what's going on here. And I'm not going to try to do this. I'm just saying, like, I'm going to post these notes. And for those of you who want to go through the derivation, you get a serious brownie point if you do go through the derivation and it makes sense to you. But I'm just not going to do it because I'm just going to say the math does work out. If you just like say, okay, my rate of forward reaction is this, my rate of reverse reaction is this. I'm just going to do a lot of algebra with these things and shuffle these things around and keep shuffling them around and doing just more and more algebra. What I'm eventually going to come up with is it's there. I swear to God, everything I just did, it takes you right here. You just follow that stuff and it takes you right there. It's just algebra, rearranging things around, basic kinetic equations, but that's where you land. I'm just saying it doesn't just come out of nowhere. It's just a simple set of algebraic steps that you take to get from just basic forward and reverse reactions to this equation. So it's not just coming out of nowhere. It comes out of genuine, the math of just kinetics. Now, I want to talk a little bit about how we go about using that in our models. Like, okay, so I've like made a fuss about how important this is. You being what I assume are mostly practical people, you want to know, what do I do with this thing that he's made such a fuss about? And so this is where I want to show you like how it modifies what you already know. So this is what you already know and is incredibly familiar to you, just like a first order growth equation, our very first population model, where we've just got exponential growth here. The more of the stock we have, the larger the number you're multiplying times R, and you're getting there. So the way you use this in an equation is simply to insert your substrate and your half saturation constant into this equation. You're just inserting it in there. And instead of saying my growth is R times N, you're saying my growth is R times this little Michaelis-Menten term here, this hyperbolic saturation term in here, times N. So this is a little modifier. And again, I'll ask the question, if I is much, much bigger than IK, what happens to this equation? Yes, Gigi.
Your D and over DT will be very close to R times N.
Yes, it just becomes this equation. If the thing is not limiting, if the limiting factor is not limiting, this simply becomes this, because this term just becomes 1. So just because you can look at that and start saying this is super complicated, just think of this as something that has a maximum value of 1. And if the thing is limiting, it's less than 1. And that degree that it's less than 1, you can think of as the fractional limitation. Like if this was equal to 0.9, it would mean these guys are operating at 90% of their growth efficiency. So they're 10% limited. 10% of their potential growth is limited at that particular moment. So yeah, you just want to think about this as the limitation that is caused by the limiting factor. It's actually, you could actually think of it as the non-limitation, really, because it's if this is 0.9, then it's 10% limited by that thing. So okay, so any questions on this thing so far? All right. The application of this is really any sort of situation, any process where you've got some sort of a machine that's converting some resources into some form of product. And it could be a factory that's producing widgets, where they've got a certain set of parts that come into the plant at some rate. Any of those parts could be a limiting factor. Like during the pandemic, for instance, car production was severely limited by computer chips. They became sort of the limiting factor. So everything else was there, but the computer chips weren't there in sufficient numbers, which is part of why we had the whole CHIPS Act and stuff, because it became apparent how dependent our car production was on non-domestic chip production, because that was the rate limiting thing. There just weren't enough chips, and so we couldn't produce what the plant would otherwise be capable of producing, because that was a limiting thing. If you're a predator, how many prey you have, your food, if you're a plant, nutrients, light, etc. So yeah, it's just anything that is processing stuff and needs these key limiting resources in order to process stuff. Darn it, I wanted to talk about something else that seems to be out of this show. Okay, well, I'm going to talk about it anyway, but without this being present here. I really thought I had that in this. Darn you. Well, I'm going to talk about it anyway. So I'll just talk about it. Heck with what's on. Well, actually, let me get this guy back up here. Yeah, I really thought I had that in here. Let me just search for a moment, because I really do kind of want to talk about this. Oh, too many darn files open. Take a break, stand up, stretch while I try to figure out what the heck I'm doing here. I'm going to go ahead and launch into ecosystem models because start me up. Right, okay. Right, this is where I want it to be. Help me out here. Okay, so yeah, I'm kind of slightly picking up where I was before. So we talked the other day about bottom up versus top down control, and I'm not gonna repeat that here, except to say that those bottom up controls tend to be Michaelis-Menten type situation. So when we think about this bottom up control of plants, they are bottom up controlled by nutrients. Give them more nutrients, they'll grow faster, but they'll eventually saturate. Give them more input of light, they'll grow faster, but they'll potentially saturate. Same deal with the consumers up here. Give them more phytoplankton, they'll grow faster, but they'll eventually saturate. So this brings us to the whole concept of limiting factors as a sort of bottom-up control limiting agent here. So it could be light that's limiting, it could be nutrients that's limiting, but there's some sort of limiting factor that's acting on growth. And again, top-down is also a kind of limiting factor. We see that in the Locker-Volterra equation. I've already said most of that. Okay, so here's where I wanted to go directly from where I was before. So you've got, notice how I'm changing the terminology here a little bit. So P, photosynthesis, equals P max times I, and oftentimes in biology, we use I to indicate light intensity. Sometimes we call it PAR, photosynthetically active radiation. And sometimes we call it I. I just stands for intensity in this situation. So light intensity, and there's a half saturation constant for light intensity. So we would call that IK, the half saturation for light intensity. Like I say, Michaelis-Menten tends to be super useful for modeling bottom-up type control. And here we've got P is the rate of photosynthesis, I is abundance of a limiting resource, IK half saturation constant. And the two important terms, as I've said before, are the maximum rate, P max, and then this limiting factor here. Again, this is a little bit of a repeat what I've said before, but if I is much less than IK, then basically, if I is tiny, this approach is 0, but if I is much greater than IK, this approach is 1. And so there's that transition between those two things. But what I'm trying to get to here is this idea of, how many of you are familiar with Liebig's law of the minimum? Does that ring bells with people? No? Honestly, one person. Anyone else, when I say Liebig's law of the minimum, it kind of means something to Owen. You've heard it before.
Well, it was on our quiz.
Oh, it was on our quiz.
It was
Right.
the wrong answer.
Oh, okay, right. So it was on our quiz. So you've seen it before. I was wondering, why did I put it on the quiz? I haven't thought about it yet. I put it on the quiz is a wrong answer. Right. Okay, that makes sense. So Liebig's law of minimum. So Liebig was actually a German chemist, agricultural chemist, super important person actually, 1800s, who really kind of figured out limiting, like nutrients as limiting factors in agricultural growth, and super important figure. But basically, in the generic sense, Liebig's law of the minimum is that the growth or biomass are determined by that resource which is available in least abundance relative to that organism or population's needs. So the thing that is available in least abundance is the thing that limits productivity of the system. There's also a sort of like, it's not really a counter view. I mean, Liebig's law of the minimum would kind of maybe adopt this as a friendly amendment, but it's that productivity can simultaneously be limited by multiple factors. So I want to get to helping you understand how you might actually combine multiple limitation factors in a model, because there's kind of two choices, and modelers will often switch between these two choices. They'll alternate between these two choices. So here's again, like what I was saying, like you've got a population, it's got a growth rate, it's got a loss rate, it's got light limitation. It potentially also has nutrient limitation. It could have both of those things. It could have both light and nutrients as limiting factors involved in them. And the idea here is that the Liebig version of thinking about this situation would be that photosynthesis is equal to let's say I represents light intensity and N represents nitrogen, some key nutrient that the plant growth is dependent on. So the Liebig sort of thinking about this situation would be that your photosynthesis is either going to be multiplied by this term or by this term, depending on which one is smaller. So the one that is more limiting relative to the organism's needs, that is, whichever one of these is the smaller fraction, is going to be multiplied by this in order to model growth rate in this situation. So again, we're imagining a situation, we've got a plant, it has two potential limiting factors here, light and nutrients. And Liebig's view of this situation would be it's going to be limited by that resource which is available in least abundance relative to the growth needs of the plant. So you're going to choose whichever one of these is smaller. Yes.
Why would they not?
Well, that's a good question, and that's sort of version 2. So in Michaelis in Liebig, you would choose one of those. You choose the smaller one of those things, and you do that. The alternate would be to do exactly what you're suggesting, which is just multiply them together, and that's sort of the fractional limitation or the multiplicative formulation. So it's just a different way of thinking about things. And I'm introducing both of these to you because you will see both of these in models. Some people will sort of like basically model it in Liebig's universe, and some people will model it this way. And which makes sense, really kind of depends on context. Yes. Well, if you think, again, I always go back to the soft analogies. Like, I think for most of us, we're never as fully productive as we could be. We could always be more productive. So for you right now, I'll put you on the spot, Avi. Why are you not as productive at this particular moment in your life than you could be? And I don't want like, and don't give me stuff that you wouldn't want to share with the class. But like, why are you not as what are the things that are limiting you from being like from realizing your absolute full potential right now? God? Yeah, that's an interesting limiting factor. That's one I hadn't contemplated. Well, I've certainly contemplated God. I don't know how God's a limiting factor in this situation. That one feels complicated to me, and probably more complicated than I can get into right now. What else other than the existence of God?
Stephen.
Sleep, okay. What else? Okay. Okay, right. So you've got like previous knowledge as a limiting factor, and you've got degree of tiredness as a factor. So I guess the question is, can those both act at you at the same time, or is it just one of those that's acting at a given time? Multiplicative then. That would be a multiplicative situation.
And if I have a jar of jelly, the amount of them that I can make is determined by which jar is.
Yes, excellent, excellent, excellent. These are two good examples of like alternate situations. Or going back to the factory example I was talking about, it's like if you don't have the chips, doesn't matter how much the other ones are like lower than optimal, you can't build the darn cars without the chips. You know, even though it may be the case, you got lots of metal or whatever, or bumpers or whatever it is, but you know, and you have a little bit less than optimal of something else. If you don't have the chips, you just can't build the car. So yeah, you know, different contexts, but the way to think about these things is this is the fraction of the limitation that is due to one particular thing. So if this is light intensity, this is the fraction of the limitation that's due to light intensity, whereas this one is the fraction of limitation that's due to a lack of nitrogen. So you may be a plant out there, if any of you are gardeners and you're trying to grow stuff, obviously you're shooting for optimal light. You want to make sure that your plants are not shaded. You want optimal nutrients in the soil, not just one nutrient, but you're shooting for a whole range of nutrients that are in the right balance with each other. You know, you get fertilizers that are actually optimized for different kinds of plants. Depending on what you're growing, you'll have different ratios of fertilizer, but those are trying to achieve a situation where none of those nutrients are limiting to the particular organism present. Yes.
I'm here. So, oh, wait. That is that like a number based on the other thing? Like what does the substrate?
The substrate is this, which is light intensity here, or this, which is nitrogen concentration.
Okay, but what are the variables for the substrates again?
These guys are the half saturation constant.
Okay,
These are just constants.
Right.
And the constant is kind of dependent on how needy that plant is. So if you have a plant that is, you know, some plants need a lot of nitrogen to grow. Corn, very hungry plant for phosphorus. You need a lot of phosphorus and nitrogen, but a lot of phosphorus to grow corn. It's just a very hungry plant for that, as opposed to, let's say, a legume, where if we're talking about nitrogen, it doesn't need you adding nitrogen to the soil. It would like you to add nitrogen to the soil, but it's got this, you know, colony of rhizobial bacteria, which if you pay them lots of glucose, will fix. See, this is what people don't realize about rhizobial bacteria is they are very calculating. They are very demanding of you have to feed them. I forget what it is, but it's an enormous amount of glucose. You got to feed the little buggers. Yeah, and they absolutely won't do it if you don't pay them. People think that they're just sort of like these altruistic little microbes. They're not altruistic at all. They're in it for themselves. And I just want you to understand that. They won't do it. Like people often say, like when I talk about the nitrogen cycle in the living machine, for instance, people will say, I say, you know, well, what's going on in here with nitrogen? And they'll say, well, there are nitrogen fixing microbes in there. And I say, why would a microbe want to fix nitrogen in a world in which they're living in poop, which is full of nitrogen? It's like the last thing you'd want to do as a microbe is fix nitrogen when you're living in a sea of nitrogen. There's no one is going to pay you to fix nitrogen if you're living in a sea of nitrogen. There are no rhizobial bacteria in the living machine. Or I mean, I'm sure there are rhizobial bacteria in there, but they're not doing anything because no one's going to give them glucose, because why would you give them glucose if you have plenty of nitrogen to do your thing? Does that make sense what I'm saying? Right, it's that kind of thing. Okay, I'm gonna stop right here because I've talked a long time. We are going to, I realize you're in the thick of an assignment right now. And the question is, when do I have you, is it too early for me to have you form new pairs because you're just sort of beginning to groove with your current pairs? I'm getting a definite nod on that one. So I'm not going to, even though we're going to start doing ecosystem models with this stuff, I'm not going to form new pairs today. So what I would like to do with the balance of our time is I'd like to chat with you. I'd like you to chat for a moment with your neighbor about what Michaelis-Menten means to you personally. And now that we've experienced it, like how is it relevant to your life? I want you to take for a moment, I want you to think about where can you apply this to some phenomena in your life? And then I'm going to take a moment, a couple moments to share that after you've had a chance to do that. So chat with your neighbor about where hyperbolic saturation fits into your life.
It's like trying.
Have the discussion. I'm taking it a personal sense. Where could you use this? What phenomena in your life does this relate to? You ready to share? Okay, you guys ready to share? Tom, we'll do a little round robin here of sharing. Tom.
Tire, my brother's a little flat, so sure, tired. Feel like correctly, it's like.
Right, so fuel efficiency as a function of tire inflation. You inflate your tire more, your fuel efficiency will go up. It's a situation where I think I'm not totally sure you'd want to use hyperbolic because you wouldn't want to keep filling the tire, but there probably is some maximum efficiency. I definitely feel that on my bicycle. A well-inflated bike tire makes me a much more efficient rider. So there's definitely that function. So that's cool. Continuing, Tobias?
Yeah, I mean, I think I was trying to make it more like personal and like relationships. And I was kind of struggling, but I was trying to find like limiting factors of like, I don't know, like I want to take a trip with my girlfriend to a certain place, like money could be a limiting factor, where like, schedule could be a limiting factor. I don't know.
I think those are cool. So it's so if we're thinking of it as a relationship, it's well, let's just think about it this way, because I think there's actually some really good data on this of happiness I'm making it more societal now, but it fits with what you're saying. There have been a lot of curves of happiness as a function of GDP, right? Have you guys seen these curves? It saturates really low. There's like some level of GDP for a country at which, like, there's definitely a beginning curve. If you have a really low GDP and your people are hungry, they are not that happy. But as soon as people are fed, more money does not lead to increased societal happiness. So I think that's in the realm of what you were talking about. Does that make sense what I'm saying? Like,
Yeah.
people have come up with like national happiness indicators. And they saturate very low, like as soon as, this is why this idea of more money, you know, I mean, I'm not saying that, you know, it's not nice to have more money or anything like that. But it's not gonna make you happier, because the saturation, half saturation on money versus happiness is very low. Yeah, Natalie.
In the morning, I don't feel like particularly tired, but it happens pretty quickly where like it sets in and for like hour of being awake. I did not sleep. I can feel it. It comes up, but there's only so much like sleepy you can really get where it's just like it approaches this just like I'm tired and you just feel tired.
See, I think you're concurrently thinking right now about saturation phenomena and how it plays out in a dynamic simulation. And that's good. But actually, I think what I'm really hearing you say in terms of saturation is productivity is a function of sleep. And as I get more sleep, I become more productive. And at some point, more sleep probably wouldn't help me. And then you're sort of playing out a dynamic simulation model of a particular instance of lack of sleep that fits within that curve. Does that distinction make sense? Okay, yes, Jay.
I was thinking of like social energy and I was thinking of like hanging out with people. If you're not hanging out with anyone who's been really lonely all the time. And then you have a maximum level of but okay, I need to hang out with people to like fulfill that need, but I don't that I really set up. And
Yeah, I think I'm getting that. There's a lot, I get that. Okay, we'll just keep going. I think I get that. So it's kind of like social energy. I'm not sure I know your definition of social energy, but I totally get it. Yeah, yeah.
like
More friends at some point does not help you. Okay. Right, okay. So the question is, are the houseplants, clothes, and friends multiplicative? Or are they, or is it a Liebeck type situation? You could just meditate on that one. I just thought I'd throw it, since you were posing a multi-factor scenario, I wanted to pose that question because it could be either of those.
Like, say if I spent now.
Okay, we'll take that one. Milo?
I was thinking I used to swim competitively when I was a kid. And like I would always eat big meals before I swam. And then soon I realized that was a really bad idea. But I was thinking about like level of like glucose in your body. Like you can have way too much when you swim. That's not good. But also like it has to be little, like it needs to be little. So I was thinking about like amount of food versus hours.
So maybe glucose in blood and glucose in your swimming performance as a function of glucose in your blood. And I can see you're already getting into the sort of like the photoinhibition section in your thinking of like a spot where, you know, more glucose, performance goes up, plateaus, and then you're saying at some point it's actually going down. So you've got a photoinhibition, which isn't part of the Michaelis-Menten, but can be added on. Yes.
I was. But I was also thinking about the broadly, like how this relates to, I think that is graphic eye and where I assume everyone gets into, and like finding something that works really well and being like, I figured this out. All I need to do is keep doing that and we'll keep seeing these great performance. But really often there is no one thing, and most things will not continue to that high
Learning level. Yeah.
The kind of necessity of like not having to vaccine.
Right. Interesting. Okay. Luna?
I was thinking about anxiety as a function of anticipation. Today with the housing lottery, I was like anticipating it, and as I was anticipating it, I was getting more anxious. But there was a kind of a point
But I think the problem is that I have to sort of like find.
Yeah. Yeah. I'm glad that you're experiencing cognitive dissonance about like what is a pattern of change over time, whereas what's just a relationship that just exists out there, and depending on where I fall on that curve, I'm performing differently. Because I think this is where people very often get confused. So I'm glad that you instantly went into the cognitive dissonance, because that's what's going to help you figure this out. Rosa, I'm totally putting you on the spot here.
Okay,
Do you have any idea what we're talking about here? Is this just been like, that is craziness?
I'm not. So sort of like, if I'm outside and it's, you know, I can be in person. I start to feel my hands don't close the same way. And then they sort of start to pass out.
Yeah, I think you've also got a time dependent phenomenon going there a little bit. Jacob.
I was thinking about how like mine is also,
Okay, Owen.
or at least
Well, I'm glad you guys are realizing that.
I was at least somewhere. I was thinking about like drawing at with like a pen on paper,
Right.
and how as you draw more, you are filling up the page more, and you can't really draw more from the same page. And eventually you hit a point where there's no room left on the page to draw on.
Right. It's got some similarities, but I think it doesn't have the fundamental characteristic of a bunch of different possible levels of this thing, and a rate that is a function of where you are in that line. Does that make sense? New econ? New ink on.
Yeah.
Like space left to draw and keep drawing it off the page.
She was also kind of, yeah, I was thinking. I wouldn't necessarily.
Well, how about this? It's like rate at which you can draw as a function of how full the page is with stuff already. You know what I'm saying? Because that is a sort of like, if I've got more space, I can, draw a lot of stuff. And as the page gets full, it's just harder to, there's less room, so I draw at a slower rate. Okay, you're on.
This also might be temporal, but I'm thinking of like practicing specifically in practice music, and like the quality of your output, or I mean it could be a lot of things, but I was just thinking of like, the more times I play or sing something, the more second nature it becomes. But there is an extent to which that happens.
I think that's perfectly good. If you just frame it as hours spent practicing and performance. So hours spent practicing and performance, I think it's quite saturating. At least, yes, time is the substrate in this case, right? So that's a little tricky, but yes, time is the substrate in that case, where it's hours spent practicing, and probably you want to put a frame on it. So like hours spent practicing per week versus versus musical performance, where if you spend no hours per week, you've got a low level of performance, but at some point more hours per week isn't going to get you further. Okay, perfect. I appreciate that we're landing in a little bit of cognitive dissonance around that issue of like, what is a dose response relationship and what is a pattern of change over time. So good stuff. Have a great weekend. Yeah. How's this exercise going? This one should be easier than the population model one that you're on right now. Is it fun? Are you guys having fun with disease? I really personally enjoy disease. I'm gonna try to deal with that situation right now, Avi, while I have a couple minutes before my first person.
Yeah.
It is a second order situation if that's where you're going.
Oh. Yeah.